Hi everyone, today I'm presenting our new result on rationally inattentive path planning via RT star algorithm. In this presentation, I'll start by explaining the motivation and continue by describing the problem formulation and our proposed algorithm. Finally, I'll conclude by providing some simulation results and their associated discussion. The main motivation for doing this research is observing the fact that oftentimes the autonomous agents select paths that are not simplest to follow. By simple paths, I mean the paths which can be followed by few sensing actions. For instance, consider an example shown in this figure, where a robot starts from the origin and seeks to find the shortest path to move toward the target position without colliding with the obstacle. As the robot moves, its uncertainty grows. The circles in the figure represent the uncertainty. The robot can perform measurements to shrink the uncertainty. As it can be inferred from the figure, pass A is shorter than pass B, but the robot should perform several measurements to follow A. This is an example where the shortest path is not always easier, or I'll say simplest to follow. Several sensing action requires high computational efforts and long processing times. The increase in computation also implies increase in energy consumption. Considering these downsides of performing frequent sensing action, the main objective of this research is to incorporate the expected perception cost in the path planning algorithm in a general manner. By a general manner, I mean without using any concrete sensing model. The second objective is to develop a numerical algorithm to find the shortest but simple paths quickly. In this research, we develop a flexible algorithm in which the importance of perception is tuned through the parameter alpha. The larger alpha puts more weights on perception cost. For example, the shown videos are the result of our proposed algorithm for different values of alpha. As it can be inferred, for alpha equals 0, the robot selects the path which has the shortest Euclidean distance. But by increasing alpha, it selects the paths which have higher Euclidean lengths but require fewer sensing actions. Our idea is basically defining a path length which jointly penalize the amount of sensing needed to follow a path and a distance traveled. We quantify the required sensing by using measures from information theory. Our approach is inspired by the famous paper, Implication of Rational Inattention. It is closely related to rationally inattentive control, which jointly design control and sensing policy such that the minimum bits of information is collected to achieve the desired control. We use the body of literature around rapidly exploring random trees and develop an RRT star-like algorithm incorporating our proposed path lengths. The proposed algorithm is called RI-RRT star. In this research, we assume the robot's dynamics are governed by the linear equation 1, where the robot's configuration is X and U is the common input. The robot configuration is parameterized by Gaussian distribution, so the path planning is formulated in uncertain configuration space, I mean the product space of real valued vectors and positive definite matrices. The shortest RR path problem is mathematically formulated as equation 2, where in the obstacle field environment, like the one shown in the figure, we seek the shortest path that starts from the start node, reaches the goal region, and maintain the confidence bound, I mean chi-squared, on the probability of colliding with obstacles. In this research, we define the RR cost for a string from zk to zk plus 1 as the weighted sum of the control cost and information cost as described in 3, where alpha, as it was introduced earlier, is the perception cost associated with gaining 1 bits of information. The control cost is defined to be the Euclidean distance between xk and xk plus 1. In the transition from xk to xk plus 1, the covariance propagates to pk plus the distance traveled times w, denoted by p hat k here. We define the information cost to be the entropy reduction from p hat k to pk plus 1, which shows the minimum required bits of information for transition from p hat k to pk plus 1. It is worth noting that the information cost and consequently RI cost are asymmetric. So far, we have defined the RR distance between 2 points in uncertain configuration space. This RR distance can be used to define RI cost for paths like the one shown in the figure. For these paths, we define different partitions like the one shown by the green dots, for which the cost is defined to be the summation of RI distance between consecutive points. The RI cost of the path is defined to be the supremum of the cost over different partitions of it. As stated earlier, we use RT star algorithm to solve the shortest RR path problem, but theoretical guarantees of RT star algorithm, like asymptotic optimality, which is actually the convergence to the shortest path, expect the continuity of the path cost. So in next slides, we show the proposed RR cost is continuous. For special class of paths where W is greater than the rate at which the covariance changes, we derive a closed loop expression for RI path lengths as described before. As a first technical contribution of the paper, we showed the RR cost function is continuous in 1D, which means that if 2 paths are closed, their RR cost is also closed. The continuity of cost for higher dimension is only confirmed by simulation. We also showed RR path costs satisfy the triangular inequality, so the optimal motion plan in obstacle-free space for moving from zk to zk plus 1 is to move directly from xk to xk plus 1 without performing any sensing action before reaching xk plus 1 and performing a single measurement after reaching xk plus 1. Such a motion plan is depicted in the figure and is referred to as move-in sense strategy. The optimality of move-in sense motion plan, as I will explain later, is used to implement branch and bound technique to increase the efficiency of RI-RRT star algorithm. Now it's a time to explain RI-RRT star algorithm. As it can be inferred from the pseudocode, our algorithm is the implementation of a standard RRT star algorithm with RI path cost. Like standard RT star, it has 4 steps of sampling, scaling, node addition, and rewiring. However, it is performed in uncertain configuration space. And since RR cost is asymmetric, the collision for the path from and to the sample point should be checked separately. Likewise, the cost of path from the neighboring node to the sample point and the cost of the path from the sample point to the neighboring node should be computed separately. The RI-RRT star algorithm is performed in uncertain configuration space, and thus it has higher dimensions in comparison with the standard RT star. So it may have lower computational efficiency. In this paper, we use the branch and bound technique to increase the computational efficiency. In this technique, after finding a feasible path to the goal region, it periodically deletes the nodes that cannot be on the optimal path to the goal region, like the blue dots, like the blue dot in the figure. Considering the fact that RI satisfies triangular inequality, to determine these non-optimal nodes, it suffices to check the condition expressed in equation 5. It means that if the cost of traversing from the start to a node plus the RI distance from a node to a goal region is greater than the cost of a feasible path from the start to a goal region, the node cannot be on the optimal path. We now present simulation results. For 1D simulation, consider the example shown in sub-figure A, where the red dot is the start and the green region is the goal region. As it is shown in the figure, the RI-RRT star algorithm has found the move and sense motion plan as the optimal path. The sub-figure B also demonstrates how the cost reduces by increasing the number of nodes in RT star 3. The simulation on the right column shows the symmetric nature of RR cost. Since there exist two paths with similar Euclidean distance from the start to the goal, I mean, one passing under the diagonal node wall and one passing above the diagonal wall. The former one requires a less severe uncertainty reduction, and thus it is selected by the algorithm as the path with lower RI cost. In summation, in this paper, we present a novel cost which accounts for both the path distance traveled and the amount of information which must be perceived by the robot. A sampling-based method, I mean RI-RRT star algorithm, was presented to find the shortest RR path. 2. The continuity proof for dimensions higher than 1 is left for future work. Several techniques can also be used to increase the efficiency of RI-RRT star algorithm, and the implementation of such techniques is left for future work. Thank you very much, and I would be happy to answer any question you may have.